Let's talk about carbon. I mean, it's literally everywhere. It's in the food you eat, the clothes on your back, it's even in you. It's the foundation of all known life, but it's an element that's just full of secrets. So today, let's peel back the layers and uncover what makes this humble element the undisputed king of the periodic table.
All right, so the first secret is a bit of a paradox, actually. We all know carbon is the backbone of millions of compounds, the very basis of our existence. But when you actually look at our planet, it's actually super rare.
Get this, 0.02%. That is a tiny fraction. That's all the carbon that makes up the entire Earth's crust, and most of it's locked away in things like minerals, coal, and petroleum.
And if you think that's small, it's even rarer in the air we breathe. In an atmosphere that's mostly nitrogen and oxygen, carbon dioxide accounts for just this tiny sliver. It's practically a trace element.
So, that's the big question, right? How on earth did this cosmic underdog, this incredibly scarce element, manage to become the undisputed champion of chemical construction and the architect of life itself?
Okay, so our investigation starts with clue number 1, the really unique way carbon connects with other atoms. See, it's not about fighting over electrons. No, it's way more collaborative than that.
So you can see here, there are basically two ways atoms can bond. On one hand, you've got ionic bonds. Think of these as givers and takers, a simple transaction. But carbon plays a totally different game. It's all about sharing.
And that sharing, that's what creates what we call a covalent bond. It's really a partnership. Two atoms share their outermost electrons, we call them valence electrons, so that both of them get to feel stable and complete, kind of like the noble gases. It's a true win-win situation.
Let's make this super simple. Take two hydrogen atoms. Each one has one electron, but they'd be a lot happier with two. So what do? They get close, share their electrons, and bam, you get a super strong, stable hydrogen molecule. This sharing, this is the secret to carbon's power.
Okay, so this whole sharing thing, forming covalent bonds, it unlocks two, and I mean two, game-changing superpowers for carbon. And these two properties, they're why carbon is, not just another element on the chart.
Superpower number 1 is called tetravalency. The easiest way to think about this is like a Lego brick, but one with 4 connection points. Since carbon has 4 electrons it's willing to share, it can form 4 strong covalent bonds at the same time. This lets it build up, out, in all 3 dimensions, creating these incredibly complex structures.
And then we have superpower number 2, catenation. This is carbon's special talent for linking up with itself. It forms these long, incredibly stable chains and rings. The bond between two carbon atoms is just exceptionally strong, much stronger than, say, a silicon-silicon bond. And that stability? That's the key reason life is carbon-based.
So what happens when you put these two superpowers together? You take tetravalency, the 4 connection points, and you add catenation, the ability to link to itself, and what you get is a masterclass in molecular architecture.
So these are kind of the basic architectural styles. Carbon can form simple, straight chains, like the stuff in natural gas. Or it can get more complex and create branch chains. And it can even loop back on itself to form these really stable rings.
Okay, now this is where it gets really, really cool. Look at these two molecules. They're both a type of butane, which means they have the exact same parts. 4 carbons, 10 hydrogens. But look at how they're built differently. It's like having the same set of Legos and building a tower versus building a car. Same parts, totally different structures, and that means they're completely different substances with different properties. We call these structural isomers.
But wait, there's more. Carbon's ability to build doesn't just stop with making skeletons out of itself. It's also a really friendly element. It loves inviting other atoms to the party, and when it does, that changes everything.
Yeah, those chains we just looked at, that's just the start. Carbon also forms really strong, stable bonds with lots of other elements. Think oxygen, hydrogen, and nitrogen. And these little attachments are what give all these organic molecules their specific jobs.
And we have a name for these attachments: functional groups. For example, if you snap an OH group onto a carbon chain, poof, you've got an alcohol. Or if you attach a COOH group, now you've got a carboxylic acid, like the stuff in vinegar. Each group basically gives the whole molecule a brand new chemical personality.
Okay, I know that was a lot of theory. We've seen how carbon builds these skeletons and then attaches these functional groups. So let's bring it all home and see how this works in something you use literally every single day: soap. Soap is just a perfect example of carbon superpowers working together. At its heart, a soap molecule is just a really long carbon chain, that's catenation right there, with a very specific functional group, a carboxylic acid, stuck on one end. And that gives it a very special set of skills.
And this is what it does. It forms a structure called a micelle. Think of it like a tiny little cage, a whole bunch of soap molecules working together to trap oily dirt. But to get how this little cage works, you have to understand the secret of just one soap molecule.
See, every single soap molecule has a split personality. It has a long carbon tail that is hydrophobic. That means it hates water but absolutely loves oil. So all those tails dive into any greasy dirt they find and grab on tight. Then you have the other end, the ionic head. It's hydrophilic. It loves water. So all the heads face outward, trapping the oil inside this little sphere, which lets the whole thing get washed away with water. Brilliant, right?
So there it is, the carbon paradox solved. Its rarity doesn't matter because of its incredible versatility. Covalent bonding gives it tetravalency and catenation, and that turns a simple little element into the ultimate molecular Lego brick. It can build almost anything from gasoline all the way to DNA.
I mean, think about it. We've built our entire world on carbon. Plastics, medicines, fuels. It is the foundation of life itself. And that leaves us with one last, really fascinating question. Now that we know its secrets, what else can we build with it? What comes next?